Math is good for you. Well, I'll take her away. Oh, jeez Louise. Drawer underneath that purple binder right there. What? As long as you're only using that for it. Okay.
I'm only using my phone for a calculator.
Okay.
Then
Did you find it?
have my word.
The drawer underneath.
Oh, drawer. I thought you said
Just didn't mean literally.
Oh, Antonacci. All right. So, first two sections, we have really looked at the history and development of the atom. So now we have the periodic table, and we are going to learn how we read the periodic table first. Okay, and really, the periodic table is much more than what is printed here. Okay, in fact, I'm just wrapping up a chapter in Honors Chem where we look at what is beyond the information on the periodic table. Okay, because it is full of a variety of things that just aren't explained to you on there. Okay, we have a whole chapter devoted to just the table itself. Anyway, we got to be able to learn the basics of it, though. We have to be able to learn how to read the periodic table. We have to learn how it's set up. We have to learn how to mathematically solve certain bits of information. Okay? So, let's start off with the atomic number. All right, so simply put, the atomic number is the number of protons within the nucleus of a particular atom. Now, referencing your periodic table that you got from my podium, it is the number that is above the element symbol. Okay, it is not the decimal number, but it's the whole number above the symbol. Okay, that is your atomic number. It is unique to each element. If you start to manipulate and remove or add protons, you are simply changing the identity of the element, and that is a big no-no a lot of times. A big no-no. Unless you're talking radiation, which we will in section 4. But for now, you don't want to mess around with protons. So the protons were discovered by Henry Moseley. Actually, I should say the atomic number was discovered by Henry Moseley. And so onto the periodic table, we are arranging the elements in accordance with the atomic number. Okay? The atomic number ultimately determines the position of which the element or a particular element will be found in the periodic table. As we move around the periodic table, left to right, top to bottom, we see the atomic numbers increase. It's in numerical order, folks. And so if we were to start at hydrogen, from top left, I'll let you right here first. Who knows what a typewriter is? So you know how you typey. Well, as you type, you're going left to right. What happens when you get to the very end? Ding, right? And it brings you back down here, but you're down a row. That's how we navigate through the periodic table. We start here, hydrogen, we go to the right, get the helium, ding. We start back here. It just goes that way through the entire periodic table, like using a typewriter. Okay? Now, on the periodic table itself, we are looking at atoms of elements that are neutral. Okay? Now, when we have a neutral atom, we talked about this, I believe, 2 days ago. What two particles equal each other in a neutral atom? Talked about this on Tuesday. What two particles of an atom equal each other in a neutral atom? Protons and electrons. Very good. So the protons equal the electrons in a neutral atom. Electrons being negative, protons being positive. and they had the same magnitude of charges but opposite, so they cancel each other out. We look at lithium. Lithium's atomic number is 3. I want you to find lithium on your periodic table. Find lithium on the periodic table. Where is it? Yay. Very good. Right here. Okay. Again, we're assuming that it's neutral because we're looking at the periodic table. That means that its atomic number being 3, that means that we have 3 protons. But also, being neutral, we have 3 electrons. With me thus far? Excellent. Now, 4th hour, I had to talk them out of wanting to memorize this whole periodic table. I was like, guys and girls, there's a lot of information. We don't care. We want to memorize the symbols, the order, the atomic number, the mass number, everything. Please? No, we don't have the time for it. I'm just kidding. I'm just kidding. No, I actually scared them when they asked that. I go, why wouldn't we? It'd be a great time, great thing for you to learn. But no. Okay. So we're taking this. We're going to fill this table out together. Okay? You're going to make sure that periodic table is right in front of you and fill it in as we go as well. All right. Element symbol, PB. I want you to find that and tell me the name of this element. Lead. Very good. Its atomic number is 82. So we have to fill out number of protons, number of neutrons. How many protons do I have? 82. So there's going to be a lot of me just calling out to the class for everyone to participate, okay? How about electrons? 82. Very good. All right, we're off to a hot start. But now we go to the next row, and this row is almost empty with the exception of a single number. We have 8 protons. So let's start off with determining my atomic number. 8. Yes. Let's go to the electrons now. 8. Very good. First of all, what is my element?
Oxygen.
Oxygen. What is the element for oxygen's symbol?
O.
With one number, you answered 3 questions. Wouldn't that be nice to have everything just that simple? Right? But it's not always that simple. Let's go to the last one. We have 30 electrons. First of all, we got to fill this 3 out. So what do you want to start with? 30 what? 30 protons.
30.
30 what?
Atomic number.
Atomic number. What is element 30?
Zinc.
Zinc. What is its symbol?
Yeah.
Worked up a sweat on that table, didn't we?
That hurt my brain.
Well, at least the brain is working, though. If it hurt, it's still working.
My brain box. Oh, the
So
pain.
we are going to take this and continue talking about this. Now, what we're going to take a peek at now is something that I mentioned when we were talking about John Dalton in section 1. Okay, you know, we got a whole bunch of people in section 1, but John Dalton was one who gave us what I call the postulates, or the 4 statements. Okay, and one of his statements was that all atoms of an element are going to be exactly the same. And I said, yeah, to some extent that is true, but it was true when he made the statement. And since that statement was made, we had now discovered the notion of isotopes. Okay, and so that's what we're going to talk about here for the next few slides, are isotopes and mass numbers. So, an isotope, defined as an atoms, I should say, with the same number of protons but different number of neutrons. Again, it's very important that you remember that when we are looking at atoms of the same element, that again, their number of protons remains the same, because that is unique to each element. The only thing that's really going to change is the number of neutrons. Let's look at potassium. Okay. Some elements on the periodic table, they have just 2 isotopes. Some elements have 3 or 4. Okay. It just depends. So let's look at the three isotopes of potassium. Every single one of them contains 19 protons. Even though, as you'll see here, the number associated with the isotopes changes. So, in addition to learning about isotopes, we are also going to learn about the two different ways in which we can name isotopes. And you're looking at one right now. Potassium 39. Don't forget the dash. Potassium-39. Okay? Where we actually list the name of the element, followed by the mass number, I should say the rounded mass number of the element or the isotope. And the term mass number, you're going to learn here very soon what that consists of. Okay? So potassium 39 has 20 neutrons. Potassium 40 contains 21 neutrons. Potassium 41 contains 22 neutrons. Now, I'm just going to put this little thought in your head, and I want you to think about it while we are continuing on. Taking a look at these three isotopes, potassium 39, potassium 40, and potassium 41. And you see that, their number of neutrons changed. But think about where that number of neutrons is coming from. How can we solve that? Yeah, it's just a thought that I want you to have. Don't answer it yet. How are we able to determine the number of neutrons in each one of these isotopes? Okay. Now, in nature, we have since discovered isotopes. There can be multiple isotopes for every element. We then start calculating what's called the relative abundance of each isotope. And we found that once we've kind of determined the relative abundance, it was constant. Our calculations and our discovery was pretty spot on. Again, going at the three forms of potassium, it was found that potassium 39 makes up 93.25% of the abundance of potassium. Potassium 40 makes up 6.7302% of the abundance of all potassium. And lastly, potassium 41 just makes up a fraction of a percentage of all the potassium. Now, take a stab at this. If you were to add those three percentages up, what do you think you'd get? 100%. Yeah. It's 100%. So these three isotopes make up 100% of all known potassium mass that, in the universe as far as we know. Okay? And that the majority is this particular isotope. And you'll see this a little bit later, but just to also reiterate it when we get to that point, that see that number on the periodic table that is below the symbol, it's got the decimal? See that is the mass number for that particular element. The mass number at the bottom of each box is the average based on the relative abundance of all known isotopes for each element. So if you find potassium, which again is element number 19, okay, and look at that mass number, okay, 39.0983. You notice that that number is closest to this number than it is 40 or 41. That's because of its percent abundance. The larger relative abundance that a particular isotope makes up, the closer that average mass number on the periodic table will be to. And that thought, that idea, that notion is a way for us to check when we start to do certain calculations, make predictions, make calculations based upon those percentages, and we can confirm that looking at the periodic table. All right. So this next slide, dealing with the mass number, is based on that thought that I had you think about while we were talking, and I said, okay, how did we calculate the number of neutrons here for each of these isotopes? Okay. The mass number is simply the sum of the protons and neutrons in the nucleus. So we simply, to calculate the mass number, take the number of protons, add the number of neutrons, and that is our mass number for that particular isotope. So if we went back to the previous slide, how did we calculate the number of neutrons? What did we do mathematically? Beckman.
Mass number minus proton.
Perfect. We simply took this equation and rearranged it to solve for number of neutrons. We took the mass number and subtracted the number of protons. It's exactly right. And you're going to be doing that basically from here on out, that idea. Okay? The thing about mass numbers is, though, all thing it really tells us is just that, the mass. Okay? It does not determine the chemical behavior. That all boils down to the number of electrons. So, when we write isotope notation, there are two ways you can do it. You've already seen one, and that is the element name form, where you write the name of an element followed by the whole number of the mass number, just like we saw with potassium 39. The second way, the second way is known as the element symbol form, where you are going to write the symbol as it appears on the periodic table for that particular element. You then write the mass number for that particular isotope in the top left of the symbol, and then write the atomic number at the bottom left of the symbol. So for the same isotope of potassium 39, the symbol as it appears on the periodic table is K, capital K that is. Again, if your symbol only has one letter to represent it, it's always capitalized. If your element has two letters that use it as its symbol, the first is always capitalized, the second is always lowercase. So potassium 39, capital K, upper left, you have 39. That's the mass number of the isotope. 19, that's the atomic number of potassium, goes on the bottom left. Okay? So let's look at this question here. A chemistry laboratory has analyzed the composition of isotopes of several elements. The composition data is given in the table listed here. Data for one of the neon's 3 isotopes is given in the table. We are to determine the number of protons, electrons, and neutrons of this isotope. And then we have to note or name the isotope using both naming methods. So let's start with the first question. Let's determine the number of protons, neutrons, and electrons here. So what I'm just going to do, protons, neutrons, electrons. Okay? And all we need to focus on is element A, neon. So in this table, we are given 2 bits of information. And we're going to use those 2 bits of information to answer 5 essentially separate questions. First, we have the atomic number. Second, we have the mass number. Based off of that information, who can tell me, or you can all tell me if you want to, how many protons does this isotope of neon have? 10. Atomic number 10. So it has 10 protons. Let's hop down to electrons. I believe, well, it doesn't say, but neon is a noble gas. Neon will always be neutral. So how many electrons will this have? 10. Now we need to determine the number of neutrons. First off, tell me what we do to go about solving that. What are the mathematical steps to solve that? We have the mass number and the atomic number. How do we find the number of neutrons?
Mass number minus the proton number.
Mass number minus the atomic number, or which is the proton number. You got that. So we take 22 minus 10, 12. 12 neutrons. Yes. Okay. So we've answered those 3 bits of information. Last part says we need to name it using both methods of naming. So let's do the name first. So simply write the name, neon, and that little dash, and the mass number of the particular isotope you're dealing with, which here it is 22. So neon 22. That's the first form. The second form is the element symbol name. And so how I like to do this, and you can go a different approach, but I always like to put the symbol first, okay? And then go from there. So what is my symbol for neon? Ne. Okay? Now, since we're doing the element symbol version, what 2 other bits of information do we have to include here? The atomic number, the atomic mass. Okay? So let's go with the atomic mass. Where do I place the atomic mass in this form?
Under NE.
Huh?
Under NE.
Not under NE? Top left. 22 goes up top left. That leaves us with the atomic number. Where am I placing the atomic number? Bottom left. And the atomic number was N. And that is how you go about the second version. So again, that one was a little quieter in terms of participation. So if you kind of got stuck there for a moment, those last 2 slides before this one, very important for you, okay? Now, that leaves us with just a little bit more information to go before we wrap it up for a day. That is a little bit of history as to how we actually measure the masses of atoms and particles. Okay? Now, we are dealing with an extremely small object, being an atom. Okay? Trying to use units like meters or inches or centimeters or anything like that is really just not going to be useful. Pounds, kilograms, nah, still not going to be useful, especially when we're talking about mass. Okay? So, they developed a new unit that is reserved only for those items at the atomic level. And so here's how they came about it, okay? They came up with what's called the atomic mass unit, or AMU for short. That is the measure of the mass of an atom, AMU, okay? It is measured as the 1/12 of the mass of a carbon-12 atom. And the reason why they came up with this standard of measurement was because they wanted an atom that was relative to the mass of a specifically chosen standard. So carbon-12 being very prevalent, very common, they decided to use that pick a specific mathematical value, and then kind of went with it. That's because, like I said, it's really small and really hard to work with things that are that small in number. So the mass of one atomic mass unit is very nearly equal to that of a proton, and therefore a neutron, even though there's a small difference. A very small difference. And here's an explanation of that difference they see. Silicon-30, okay? Its mass is not 30 even, like we say here, okay? In actuality, it's 29.974 AMU. So, you know, that slight difference does make for not so nicely rounded numbers, but ultimately the differences are somewhat negligible, where we often use the rounded versions. Okay? So, the atomic mass, as I mentioned on your periodic table, it's a decimal value underneath the symbol. It's the weighted average masses of all the isotopes that were known for that element. It will never be a whole number. Okay? And a good example to look at is chlorine. Chlorine only has 2 isotopes. We've got chlorine-35, which makes up about 75% of the relative abundance of all known chlorine atoms, and chlorine-37, which makes up the other 25% of the known chlorine atoms. And as I was mentioning a little bit ago from the potassium example, if we look at the periodic table, we see that the average atomic mass listed on the periodic table is 35.453 AMU. Again, the listed or the average relative abundance for an atom is going to be closest to one that makes up the larger percentage. So 75% is chlorine-35. The other 25% is chlorine-37. We see this, and we would expect this answer of the average being closer to the chlorine-35 because it has 3/4 of the entire known abundance of chlorine. So how do we go about solving this? Well, we do this. First, we have to know the atomic mass as well as the percent abundance for each isotope of a particular element. That will usually be given to you. Next, we multiply the atomic mass by its respective relative abundance in percent. And once we have multiplied everything that we need to, we then add up all of those products that we just calculated in B. We're going to add all of those together. Once you've added those values in step C together, you'll take that sum from C and divide it by 100. After you divide it by 100, your answer is in the units of AMU. Okay? So as the very last thing, divide by 100, label it with AMU. So let's do an example. I want your calculators out and ready for this one, then we're done. So, given the data in the table below, calculate the atomic mass of an unknown element X. Again, the X is just a variable. Doesn't necessarily. It does stand in for a known element, but that's for us to figure out. Once we calculate the atomic mass of the unknown element, we then have to identify it. And to give us a little bit of extra information is oftentimes used medically to treat some mental disorders. Okay, so let's go about the steps here. First thing is we're given the mass in AMU and the percent abundances. So as step B says, we need to multiply the mass of this isotope times its relative abundance. So 6.015 times 7.5. Give me the answer with two decimal spaces. Say 0.45. 45.11. Okay, so that's the first one. Second isotope, 7.016 multiplied by 92.5. Again, give me two decimal spaces for an answer.
$670.03.
Try that again. 648.98. Very good. So now, that's all of part B, step B. Next is we add those values together. So we'll take 45.11, add it to 648.98. What do you get? 694 point what? 09. Okay. So we've added them all up. What's my next step? Divide by 100. Okay. So what do you get? A little louder. 6.941 AMU. Perfect. So that is your mass for element X. That would be listed on a periodic table. Now, we're not done yet, though. Identify this unknown, or not this unknown, but this mystery element. Who's it?
Lithium.
Lithium, yes. That's your answer number 2. Okay. Make sure that you have all these notes filled out because tomorrow you have your section 3 review. Make sure you have a calculator for tomorrow. Make sure you have that periodic table for tomorrow. Make sure you're